Good morning, you 13s. How's it going, everybody? Right, so guys, today we're going to be looking at transition metals, aqueous chemistry, lesson 2. We're going to be starting. I know that we covered in the last lesson, we did a very short 30-minute lesson just on the acidity. And I'm going to focus, I'm going to do a few questions on that just to show you some equations. Just because I know how they tend to use those acid-base equations in exams, so it'll be nice to have a quick look at that. It's just a bit of a recap. I know we've had a week off because of the half term, so it'll be good to do that. Okay, so let's crack on, folks. Be nice to have you guys just comment on the chat. That would be lovely. Okie dokie, right, I'll swing into action. Let's crack on. There we go. And then what I'm going to do is... yeah, and then what I like to do now is turn off my camera. Let's see if my computer decides to crash. Might crash. Sorry if it crashes. It didn't crash. Amazing. There we go. Cool. Camera's definitely off. Amazing. Right, so last lesson we ended on acidity. We were talking about the pH of... oh, suddenly realized I need to... go. I need to quickly, sorry about this, guys, just got to find my other, oh, it's already running. That's amazing. And then I'm going to click, and there we go. I need to quick, there we go. Perfect. And then now what I can do is turn down the quality of that. I have poor connection. Sorry, Dixon. I'll pop out the chat at this point. Sorry, not quite with it this morning. And then I can, it might be my, there we go, that's better. Okay, right, let's crack on. I'll flip my laptop into tablet mode. There we go, right. So last lesson, what we were looking at is we were looking at the acidity. We also created a list of all the transition metals that you guys needed to know. So it's quite nice to see all these. Chromium, manganese, copper, cobalt, aluminium, zinc, iron, nickel, and vanadium. And we've covered a couple already. We've covered vanadium, yeah, which we remember is yellow, green, blue, green, violet. And the second green, the first green is not an actual transition. It's a blend of the vanadium 5+ and 4+. So today we're going to be focusing on copper. We're going to tick off copper off the list today. Just before we do that, it's just nice for me to recap. It's been a while since we've looked at this, since it's been a week. It's nice to remind us of our Aqua ions. Don't know why my computer decided to jump, but it did. There we go. It's nice to remind us of our Aqua ions. And this is a key thing here because something that I'm going to say an awful lot, and forgive me if you get bored of it, everything starts off Aqua. That's where aqueous chemistry begins. And then what we did is we talked about their additions to water in this odd observation. Can I have Winkit, can I have Julian and Tex and Tenzi? Can you guys just quickly put a comment on the chat just so I can check that the chat is all running? That would be grand. And we talked about how the transition metal ions, if they're +2, then they have a pH of approximately 5. Thanks, guys. Appreciate that. Have a pH of approximately 5 at 1 mole per dm cubed, and then the 3+ are more acidic. And what we then did was we then described how the acidity is explained. So we talked about this idea of that when the water molecules form this coordinate bond to the TM ion, that the OH bonds become more polarized. This is because the electrons on the oxygen are drawn away from it. And therefore, because the OH bonds become more polar, they weaken, and therefore you can have the release of H+ much more readily. And then we talked about this idea of the 3+ versus the 2+, and the fact that the 3+ increase the polarity even more because of where the electrons are sitting. Yep, they're being pulled, and your answer is always reliant on this term charge density. Yeah, they're going to say to you, explain why iron 3 plus, I'm going to put the question down just as an ending to our previous lesson. I had to rush off. I wasn't feeling great. So just to add the exam question on here, explain why TM3 plus is. Now they're going to give you an example. They're going to say, explain why iron 3 plus is more acidic than iron 2 plus. They're going to give you that as an example, but I'm just going to use a TM, so any transition metal. Explain why TM3 plus is more acidic than in comparison to TM2 plus is. So you have to know your numbers. So the first part of your answer here, which I'm going to then try and switch. I've gone and ruined all my pens. I should rebuild the whole thing again, but anyway. I think it's going to be, no, it's not thick. It's just not zoomed in. Okay, so answer. Yeah, number 1, it's nice to state that the TM3 plus will have an approximate pH of 3. 3 and 3. That's how you tie them together. Yeah, and a TM2 plus, you add 2. Yeah, so you learn 3 and then just learn to adapt it. pH 5. So we're stating that we know the pH. That would probably be 1 mark considering they haven't told us. Yeah, the next thing is we need to now explain why. So we'd say that the TM3 plus has a higher charge density. Higher charge density compared to 2 plus. Compared to TM2 plus. Therefore, I'd write therefore in an exam, by the way. Therefore, OH bonds in water are more polarized in TM3 plus complex, 3 plus complex compared to TM2 plus complex. Therefore, OH bonds are weaker more H plus can break free. It's also nice to mention this. This is the point that I wanted to mention in terms of the equation, and I mentioned this at the very start of the lesson. So we need to be able to write an equation to show it acting as a Bronsted and Lowry acid. Now, it's nice for me to do a little bit of overlap into acid-base theory. We know when you get to A2, they start to blend topics, and they're really tough. So if you go and have a look at, if you haven't already watched my acid-base lessons on YouTube, please go ahead and do it, guys. Yeah, so we've talked about, this is where I'm up to with the other class. I've done water. I think I've done dilutions as well. I'm up to strong bases. We're doing really well, actually. And what we did is we talked about the different styles of equations that we get. And we talked about these ones. So here's your dissociation equations. Yeah, so this is just where the acid breaks free. These are all strong ones. Whereas what we're now realizing is these are all weak because they're all partially ionized. So let's choose iron 3 plus. Why not? I ought to focus on copper since we're doing copper today. So copper, Cu, everything starts off hexaaqua. Everything. I love the fact that I said hexa and wrote 5. Yeah, everything starts off hexaaqua. So this copper 2 plus solution at 1 mole is going to have an approximate pH of 3 plus 2, 5. It's less acidic than it would be if it was a 3 plus. Now what happens is the equilibrium, this tells us that it is partially ionized. You are not allowed to say not fully. You have to say partially. People always ask me, partially ionized. There you go. It's partial. You can't say not fully because not fully could also technically apply to no dissociation at all. Whereas partially tells us some of it has, the sodium, but not all of it. So avoid not fully. It's partially ionized. Right, so what's going to now happen is I'm going to lose H+. So this is the the Bronsted and Lowry equation, otherwise known as the dissociation equation. Right. And that's now +1, and there's my H+. Right, so that's what's causing the pH to be 5. Yes? So the reason why the charge is, and it's nice to see the conservation of charge, by the way. I love the conservation of charge. Yeah, on this side, we have an overall charge of +2. And on this side, we have an overall charge of +2 as well, because we've got a +1 and a +1. The reason now the transition metal hasn't changed oxidation state, the reason why, of course, it now appears different is because we now have an OH- ion attached as a ligand. Now, that's going to cause a change in color, just to be aware of that. Yeah, we've now changed the ligand. Remember, 3 things that change. You realize that the whole of acid-base theory, the whole of transition metals is all interlinked. Everything's linked together. Wow, I really am zoomed out here. I feel like I want to zoom in more. Yeah, just to remind you that the factors that change color of complexes are these guys. Yeah, color, and it's the first 3. So that's the coordination number. Coordination number. Yeah, and this is not happening in this particular equation, because if you want me to draw it out, I can do Cu2+ bound to water, bound to water, bound to water. I can even do it 3-dimensionally. Draw it as sticks and then turn that one into a wedge, turn that one into a wedge, add your dashes. They'll allow it. It's the way that's the way you should do it. So the coordination number in the original Aqua is 6. Now, these are all H2Os. We know that. These are all water molecules. And what happens during the dissociation, I'm just going to get rid of the coordination number bit. So what's happening during the transition metal ion hasn't changed size in any way. It's still +2. If I just draw all my lines on again, what's now happened is that turn it into a wedge. It's nice to practice the 3D bit. Water. Let's do this one as an OH-. Yeah, water. Now we know that because that did have a H attached to it, this was water. Here's what's actually happened here. Yeah, that electron there is broken away, and that H is then snapped off and disappeared like that. So this is now formed OH-. Yeah, so the overall charge drops, but the coordination number has stayed the same. So the coordination number has remained the same. Oxidation state has remained the same. The coordination number is still 6. I can color code this. Yeah, the coordination number is still 6. Yet the oxidation state is still the same. So that hasn't changed. What has changed now is the type of ligand. So that's the one that's now caused the change in color. Now, it's only a subtle change in color, but it is a change in color. This can be measured on a colorimeter. You can see the 2 peaks in the greens. Sorry, in the blues even. Okay, so this is the dissociation equation. Just want to quickly mention the Lewis equation. This is me doing a little bit the Lewis equation of acid-base. This is me doing a little bit of acid-base theory in transition metals. It does come up. Lewis equation, I'll put acid-base. Yeah. So you guys should probably recognize this from your acid-base lessons, but I'm not sure if you guys have started yet. So the difference being now is this. Everything starts off Aqua. In aqueous chemistry, everything starts there. And in Lewis, we have to now add water in. Yeah. So what's now going to happen is we now need to transfer H+ over to the water, so we're going to form H3O+. Plus, that makes more sense. There we go. 5 OH. Notice that I've put the OH in a bracket this time. They don't care if you do or not. There we go. So this is showing, I've suddenly realized I think I've just made a mistake. Because Bronsted-Lowry talk about proton transfer. That's not a Lewis. Sorry, I do apologize. Lewis is electrons. This is a Bronsted-Lowry equation. This is the dissociation. This here is the dissociation equation. I'm going to make my pen a bit thicker on that one. This is the dissociation. Yeah, the word dissociate, yeah, it means to break apart, which is what it's doing in this scenario. This is the BL equation, the Bronsted-Lowry. This is the Bronsted-Lowry equation. Just to confirm that, it's always nice to do it. Yeah, so I talked about this here. Here's the dissociation. Oh, Bronsted-Lowry and dissociation. Where's my Lewis? Making me move stuff. Let's go to the next equation, weak acids. It's nice to see conjugates. I've not mentioned the other one. It's a proton donor. I think I've made a mistake in one of my lessons. Ooh, I hate admitting that. It does annoy me. I'm at a loss as to where my equations are. Nope, that's AS Organics. Oh, right, the Lewis equation. What, the BL equation? But Lewis is about electrons. I think I made a mistake there. I'll get back to you on that one. Anyway, I think that's Bronsted-Lowry. Proton donor. Dissociation. Yeah, Bronsted-Lowry. The reason being is it needs to act as a proton donor. Now, in that equation here, it's not actually acting as a donor. It's not giving this to anybody. Yeah, that's just dissociation. In a BL equation, there's no Lewis. I've made a mistake in the previous group. In the Bronsted-Lowry, you've got to show that it's being donated to somebody, which is, of course, water in this case. You only have to, that equation, by the way, I don't want you to get lost in that equation because you don't need to use it very often, only when they ask you in an exam. Otherwise, essentially, you ignore it. Okay. So it's nice to show it from an acid-base perspective. If you want to see a mechanism for this, now, by the way, you wouldn't. This is actually this mechanism. I'm just going to show you the mechanism. It's nice to do it. I love organics. Mechanism. So the mechanism by name, the mechanism name is called proton transfer. Now, you do not need to know this one, proton transfer. You do not need to know this mechanism for A-level, although they have actually asked it, never the name of it, but they've asked students to draw it at times, amazingly. Now, you shouldn't really do a mechanism for this because it's not organic, but it does still have a mechanism. Just to show you it, I'm just going to water. I think I may have shown you this already. Turn that one into a wedge, turn that one into a wedge. Yeah, there we go. So I'm just going to do this one as my water. Made this one the one that I can see. Yeah, so what's happening is this. Water, 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 water. What's happening is another water is coming along and acting as a base. Yeah, it's taking that H plus and those pair of electrons is rolling back. The role of this guy here is a Bronsted-Lowry base. This is a base. It's accepting a proton. Yeah, that's its role. Yeah, it's acting as a base. And it's just taking a H plus off. That's all it's doing. And if you're wondering why I can do this, well, if you consider that this bond, thanks to the 2 plus ion, yeah, the electrons on this are way down here. The polarity is massive. Yeah. And of course, this one is slightly positive and slightly negative as well, because the water always is. So it's going to have a bigger, flipped over, got the signs wrong. There you go. And so this is going to have a big attraction to that. And when it collides with it, it can form a bond which has got a greater strength than the one it is in the complex. So that's why. Anyway, but that's called proton transfer, that is. It's quite nice to draw out a proton transfer mech. We don't often do those in A-level chem these days. Got deleted a while ago. It's a bit sad. Okay, so going back to my lesson today. Right, so today's lesson. Oh, I haven't created it. I've done it on YouTube, but not created it here. So this is, now what we're going to do is we're going to drop into, this is aqueous chemistry. Oh, and now I've zoomed right in. Oh, let's zoom out a little bit, shall we? So this is aqueous chemistry. Aqueous chem. We're taking a particular focus. This is lesson 2, and we're going to focus on copper. Cool. Learning objectives. Number 1. It'd be interesting what I put my learning objectives because so let's do. You need to know. You need to know copper's colors. Yeah. Oh, I don't want them to be different. Hang on. Oh, I've turned off my Bluetooth on my laptop. Give me a sec. I'm just going to turn my Bluetooth back on. It just means that I can go back to my. Come on, mouse. Come on. There we go. It's back. I've got my mouse back again. My learning objectives. Not in edit. There they are. I'm just going to copy and paste those. Copy. There we go. Let's get rid of that. Let's go back to this. There we go. And then past. There we go. It's nice to have them being the same as what I've got on YouTube. Okay, delete. Amazing. So we need to understand the color table. Right. I'll explain the color table to you straight away. Let's give my first learning objective. It's not going to help me. Okay. Let's get rid of my mouse. Don't need my mouse anymore. Okay. Understand the color table. Know copper's colors and write equations. Right. Okay. So the color table. So we've got a whole load of transition metals that we've got to know about. And what we need to be able to do is we need to learn over 50 colors. Now, in order to do this, the way I teach it is you learn them in strings. Yeah. And the strings of color are based on the color table. Now, you'll find this in your textbook. Let's go to this one. So, color table. So, here's how the color table works. So, in column number 1, you have the hexa, aqua, ion. Hexa, aqua. Do you know what? Yeah, and then let's stick to copper. Cu brackets H2O6 in square brackets 2+. There is the hexa aqua, color number 1. And for copper, of course, it's blue. But funny enough, you just call it blue. It's actually a pale blue, but you just kind of call it blue. What that means is they're using this one. They're using this blue as kind of the reference blue. So yeah, and anyway. So the next thing is what we now add to it is we now add a small amount of sodium hydroxide of NaOH, a small amount. Now, this is where we start to talk about its acid-base properties. We know that copper is acidic, and it's going to therefore react with sodium hydroxide. So what's the equation going to look like at this point? This is now going into my third learning objective, being able to answer equations. So let's write the first equation for this one. Cu, everything starts off hexaaqua. That's where everything begins. All of your equations, unless stated otherwise, are going to start there. Right, we're going to add sodium hydroxide to this. Now, in reality, we know that the sodium ion is a spectator. Sodium never does anything in chemistry. It's boring as. Yeah, it really is. It never even does anything in electrolysis unless we're in molten salt. Otherwise, it's just spectator. It never does anything. Spectator ion. There we go. So we don't include it in the equation. Yeah, it's nice to have that note there. Now, the cool thing about this is we have added a small amount of this. Yeah. So a little. That's quite often what I like to put. Little OH minus. So what this is going to do is it's going to react with the copper hexaaqua. And the question will be is how many OH minuses are going to react with the copper 2+ hexaaqua? And the answer is in the equation. When you have a little, what happens is the number of OH minuses will always match the charge. So the charge that I have here is going to be matched with the number of hydroxides that are going to react with it. So what's going to happen in one direction, I'm going to now form this guy. Cu, 4 waters are left, but now I have 2 OH minuses. And what you'll notice is the charge has gone. Now, this is really important. This is a nota bene, very important nota bene for your notes, folks. I'm also going to get 2 waters. Now, can I just point out, if you look at that equation, it would, by the way, before I forget my nota bene, right, loads of nota benes here that need to go on at this point. I'm going to do them underneath this equation. Right, nota bene number 1. Little OH minus always creates a neutral complex. Because what it's doing is the number of OH minuses matches the charge. They're removing 2 H pluses, meaning I'm going to result in a neutral complex. Second nota bene, neutral complexes are precipitates. It's going to form a solid precipitate. If you're wondering why, those are my 2, these are so important in transition metal chemistry. Yeah, if you're wondering why, the reason being is if the complex doesn't have its charge, then it can't attract the water molecules. And if it doesn't attract the water molecules, then there's going to be no enthalpy of hydration. Yeah, we know that if you have, this is from your studying of solubility. If you have anything with a charge that forms an attraction with water, yeah, this is an ion dipole attraction. This is called an enthalpy. This is the heat energy released on hydration. And that heat energy will go into breaking up a lattice and help things dissolve. Now, in this case, yeah, as soon as it becomes electrically neutral, that attraction vanishes. What that means is that what will now happen is these massive molecules with big MRs are going to group together due to van der Waals forces, and they're going to form precipitates. Yeah, they're not going to be forming salts the way that we normally would because it's no longer charged. So it's not going to be an ionic precipitate. It's going to be a covalent precipitate held together by van der Waals forces. Also, potentially, no, you won't get would you get hydrogen bonding between them? I don't see why you wouldn't. There's quite a high ion-ion repulsion in that particular, but anyway, van der Waals forces is the main reasoning. But you now form a precipitate. So a state symbol now appears, which is super important. Okay, so we can now use this. So just to show you this as a general, because I've used copper as the example since we're doing copper today, but just to show you a general equation for this. Transition metal, let's put 3+. If I reacted it with a little amount of OH, sodium hydroxide, the number of them would be 3. I will form, and of course, everything starts off hexaaqua. What I should have done is TM brackets H2O6 brackets 3+. It doesn't matter what the transition metal will be. I'm going to form TM bracket H2O3 OH3. They're going to match, cancel out the charge. No charge here. Forms a precipitate. Before it was aqueous, and I get 3 waters spat out the other side. Now, the next thing to mention is this equation here looks like you could call it ligand substitution. So when we were doing transition metal chemistry earlier on, we were doing complex chemistry. we were talking about and writing equations. We were writing equations for when we had ligand change, things like this. Yeah. So when we were doing equations for ligand substitution, yeah, what you realize is that the mechanism is subtly different. From a mechanistic point of view, what's happening here is the Cl- is attacking it with its lone pair and water breaks free. That there is ligand substitution. However, this is not ligand substitution. This is acid-base reactions. This is now aqueous chemistry. This is an acid-base reaction. Acid-base, not acid-base reaction, not ligand substitution. Yeah, that needs to be really clear, folks. There is a difference between aqueous chemistry and complex chemistry. Please be careful. So in our table, in our second column of the table, we now get Cu, and we now get a change in color. So we now get Cu, sorry, it should be square brackets. Cu, 4 waters left, and 2 OH minuses now attached. So that was a small amount of NaOH. I'm going to put NaOH little. I prefer that. It's easier to remember. NaOH little. Okay, and we now form a blue precipitate. Now, can I just point out, by the way, it's almost identical in color. It's slightly darker, and I mean, like, there's a tiny difference, but in reality, it's not the color here that you need to recognize. It's the fact that we're forming a blue. That's an aqueous blue, and that's a solid blue. Looks like blue snot, by the way, if you're interested. Let me show you what this looks like. Yeah, so copper precipitate. They'll show us the one we want to. Images. There we go. That's what it looks like. So it starts off this pale blue aqueous and forms this pale blue solid, this gunk. It's not particularly nice. By the way, please ignore the dark blue at the minute. We haven't got there yet. I know it's coming, but that's the blue I need you to recognize. That there is OH minus a little. Okay, so now what we're going to do is in our chemistry, we're going to now do sodium hydroxide lots, excess. So we're going to add a boatload more sodium hydroxide. Now in copper's case, nothing now happens. And unfortunately, you've got to know these. Yeah? The same one appears. Now, there is a rule I like to teach, but the rule doesn't always apply, unfortunately. There are a couple of exceptions to the rule. And that is, if you have a 3+ transition metal. So here's your 2+. So, okay, I'll try and explain this. If you have a 2+, see, here's what could happen. Here's the options. We could have had Cu4OH2. Do need the brackets for the OH now. Yeah, there's the neutral solid. We could have, if we add excess sodium hydroxide, excess OH minus, we could remove another one. Now, if we removed another one, right, look what happens. All of a sudden, my charge reappears. I'm now negative, and I have water spat out the other side. Now, just curious, on the chat, folks, can I have all of you, please? Can everyone in this room now please predict what state that would be? What state of matter, what state symbol would follow this complex? Just on the chat, please. Just give me a heads. Just it's nice for me to check that you guys are still there. And it's always nice to get a little bit of input from you guys in the lesson as well. It's always nice. Well done, Julian. Thank you for being there. That's great. Tenzi, well done. Absolutely right. Since it has a charge. Well done, Winkit. That is absolutely correct. That's the whole point of my rules, the nota bene. It has a charge. Therefore, it will be aqueous. So what that would mean is that if this reaction did happen, if this reaction happened, we would go from a situation, from a precipitate, from a blue gelatinous precipitate, it would redissolve. It would vanish again. All of a sudden, it would disappear. Yeah, and it doesn't. Now, the rule here is, this is another nota bene. 2 plus TM2 plus complexes are not acidic enough to redissolve on excess. Now, there is an exception to this rule, which is irritating. Iron 2 doesn't. Pink, blue, blue, blue. Cobalt. Does cobalt? Pink, blue, blue, blue. I don't think it does, actually. Oh, but it changes color. It darkens on excess. Oh, no, so it's actually correct. It does stand... Oh, no, zinc. Oh, zinc does. I knew there was an exception. We'll talk about this later on. Anyway, so yeah, it's a great rule. Stick with that. You learn that rule, then add the exceptions onto it. Yeah, we'll come back to that. Once we've gone through all of our metals that we need to, you'll see it. So we've done sodium hydroxide a little, sodium hydroxide excess, no change. I like it. Still got a gelatinous blue precipitate. It's nice to mention the word gelatinous. They do like gelatinous. Yeah, these are gelatinous. I can't spell gelatinous. Gelatinous? Is it gelatinous? Gelatin. Gelatinous precipitate. Yeah. Anyway, not that it really matters. It's just nice to mention it. So, right, now we've done 3 columns of our table. So far with copper, blue, blue, blue. Next one, right, ammonia, a little. Right. I've suddenly realized today's lesson is going to be taken up with predominantly going through the table, but I realize I am doing the equations as well. So it's nice that we're kind of doing these all simultaneously. Right, ammonia, a little. And I love the next nota bene is so important. So guess what ammonia can act as? It can act as a base in the same road that does. Yeah, the 2 littles. Here's a great fact for you, folks. Nota bene above this one. The 2 littles. Oh, it won't let me. It's because I'm at the top of the sheet. The 2 littles are always the same. Always. No exceptions. How cool is that? H2O4 OH, and the reason being, yeah, and that's going to form a solid blue precipitate, yeah. So the reason why, the reason why is because it's going to act as a base. I can show you that mechanistically if you like. I'm just looking to see if I can find it. Now, I'll do it via an equation. So here's what's happening. Here's my equation. Everything starts off hexa aqua. I'm going to say that so often until you guys feel sick. Oh, guess how many ammonias react with it? 2. Because when we're in a little, the big number in front of the base is always the same as the charge. I love these rules. You are writing the wrong ligand. Mr. Duncan, you are writing the wrong ligand. Ligand? What? Ligand? Am I? No, I'm not, Winkit. No, Winkit, I'm not. That's the point. You'll understand in a minute when you see the equation. Right, I've written it too big. Damn, not that it matters. So the ammonia is going to act as a base, not as a ligand in the little scenario. So what do I get? That's the Winkit. You literally just made my point. It is not acting as a ligand, it is acting as a base, and it is taking 2 H pluses. Yeah, you literally, and therefore I have no more charge, and therefore I'm going to have my same blue gelatinous precipitate. Love it. We went from blue aqueous to blue solid. In the littles are always the same. Always, no exceptions. The littles are always the same. I always like that. Makes me happy. So, let's do the colors of copper. Blue, 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 blue. Now what? Right, now, next part of the table is ammonia in excess. Now, this one is special. And by the way, when I say special, I mean really special. It's very odd, this. So copper, there are actually a couple of others that do this. I don't think you need them. I think manganese might actually do it, annoyingly. But copper's the one that they're going to ask you about. I'll show you why. Right, now, in excess, we're going to have a situation where we're now going to get ligand substitution. It's no longer acting as a base. Yeah, in reality, of course, right, by the way, this is, in sodium hydroxide's case, it's never ligand substitution, ever. It's always acid base. But this one now goes through lig sub. This now is ligand substitution. Yeah, this is very important. Right, so now let's look at what now happens, because copper is special. And I mean really special, genuinely. So here's what happens. So copper starts off as the hexaqua. Now, in the first scenario, the ammonia acts as a base and takes away 2 H pluses. Yeah, acts as a base and takes away 2. That's acid-base, proton transfer. Yeah, there we go. Proton transfer. Now, this was the little scenario. Now, we drop into excess and things change. So the copper now does something very unusual. So we have waters. This is now OH minus ion bound to it, an OH minus ion. Yeah, water, water, water. Now the ammonia acts as a ligand and they swap in. Now copper is very special because it doesn't go through complete replacement. Copper forms this. Now you're going to ask me why. Yeah, and in reality, the reason why is because copper is quite an unusual, has a quite unusual structure. Because what now happens is the axial bonds, these are the axial bonds. Yeah, these bonds here are the equatorial bonds. And it turns out in copper's situation that the equatorial bonds, I'm just going to write NH3, makes it easy for myself. Yeah, the equatorial bonds are shorter than the axial. And you get this scenario. Right, now this, and since they're shorter, they can go through legs up to the middle, but they won't be able to kick off the waters on the axials. Go figure. Yeah, it's because the bond isn't polar enough due to its extended length. So what this now means is you now get this brand new equation, which we will now write down. Get rid of all my stupid mechanistic pictures. Right, a new equation. I know we're coming to the end of the lesson. I'm nearly at the end of my table, folks. So we start, everything in life starts out hexaqua. In life. Started off as a pale blue aqueous. Yeah, pale blue aqueous. I'm now going to add, right, now I'm going to add 4 ammonias. Right, 4 ammonias. And yes, by the way, it is in equilibrium. It is. Now, by the way, this is actually done using conc. You have to use conc ammonia to do this. If you use dilute, it just doesn't do anything. What you now get is the tetraamine diaqua. How weird's that? Tetraamine diaqua copper 2+ and 4 waters. So we get this brand new equation and we get this very unusual complex because there are 2 waters left behind. It's very odd. And this has a beautiful ink blue. color. That's what it looks like. And guess on the chat, please, what state symbol's going to go with it, please? What state symbol? Amazing. So we've now got blue, 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 dark blue, 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 dark ink blue, dark blue. I prefer ink blue, by the way. Aqueous, it's a winner. Isn't it great that you can now predict? You can predict states of matter in terms of transition metal complexes. If it's got a charge, it's aqueous. Love it. Dark blue is what you're going to write down in your exam. If you write ink blue, they should accept it because it is the correct one. What state is yeah? What? I know. What? Julian, I completely agree. Right, last column. Last column. We're now going to react it with sodium carbonate. I'm just going to put carbonate ions. CO3 2-. I shouldn't really do that. I'm just going to go with sodium carbonate. React with sodium carbonate or sodium hydrogen carbonate. Doesn't actually make any difference, to be fair. That's why I just tend to just put carbonate ions in my column because they can give you it with either. But I'll put carbonate. Let's just put carbonate there. So now I'm going to react this with a carbonate. And what we now form, and here's a great rule. Last nota bene for today. Nota bene. TM2 pluses always form the carbonate. So for example, Cu hexaaqua, if you react that 2+, you react it with a carbonate ion, because 2+ and 2- match, it's not actually, it's because it's not quite acidic enough to destroy it. What you get is that. You form the carbonate. The 2+ ions always form the carbonate ionic. And of course, what state of matter is the carbonate going to be in? It's a solid since it has no charge. It's no longer a complex, by the way. It's just copper carbonate, which is blue-green in this case. All the 3+s don't do this. TM3+ always, I'm going to put too acidic to form carbonate. What they would do, if I did TM3+ hexaaqua, yeah, that was a 3+, because it's so acidic, it's going to react with the carbonate, turning it into CO2 and water. Yeah, and I will form the TM3+ triaqua trihydroxy complex. Yeah, it's acting as an acid. It's giving away, and that becomes a precipitate. Yeah, isn't that neat? You can balance that, by the way, if you want to. I hate not balancing it. Common denominator +6, 3, and then whatever the waters are. Probably 3 as well. There we go. So the 3+ are too acidic to form carbonates, whereas the 2+ do. So this brings us to the end of copper. Now, this is blue. You have to learn this, guys, as blue-green. Yeah, I'm sorry about that color. It is a nightmare. Blue-green, that's it. Copper carbonate. Your answer in your exam for EdXL is blue-green, and it is a solid. Yeah, blue-green precipitate. Blue-green solid, blue-green precipitate. Which is kind of neat. Right, so now can I just point out, copper now gains a whole load of oddities. So, but this is my table in its entirety. 6 colors for each thing. Hexaaqua, sodium hydroxide little, sodium hydroxide excess, ammonia little, always the same as the sodium hydroxide little. That's awesome. Ammonia excess, carbonate ions, and there's my table. Blue, 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 dark blue, blue, green, copper, done. Yeah, you've got to learn these strings of colors. The great thing is, just remember, 5 blues are a blue-green, but then the last blue is a dark blue. It's the way I do it in reality. Right, as I said, we will add copper's oddities on next time. So just to quickly show you, today we have managed to cover my color table. I am going to add on, by the way, each metal will gain what are called oddities as well, but it's not part of the table. You learn, this is all to do with the reactions they like to do in test tubes. The others are just like extra colors that you learn for each of them, but you learn these colors in a line. We've now picked up all 6 of copper's colors. We haven't picked up its oddities yet. We've got a few, yeah, but we still haven't got to quite finishing it, but we've got copper's 6 table colors, and we can indeed write equations for all of those stages. Wow, we actually managed to achieve all of my learning objectives today, guys. Very interesting lesson from my perspective. Very fascinating. It's nice to mention that picture. Yeah, you're going to need to be able to draw that picture. Yeah, put it in a bracket. So you can add that one there. That's a 2+. Dark ink blue. Dark blue. If you want to have a look at these guys, please have a look at YouTube for some of these. We would usually be doing all of these in class, by the way. But obviously we can't, so it sucks. We'll have to stick to YouTube. Right, guys, that's the end of my lesson today. Look at that, right to the wire. Blimey. I will leave you guys be. Guys, you can, I've turned off all my camera and everything. You guys can head off, enable device. Might crash my computer, you never know. There we go, it's back. And then I can go start camera. It's probably going to start off the reverse camera. There we go, I'm back, and then come back to here. Guys, I hope you found it useful. Watch it back if you need to, as many times as you like. Those equations, I'm going to start giving you these equations now, because technically these equations now apply across all the transition metals. It doesn't actually make any difference what the metal is or its charge. You learn to adapt the equation depending on the charge. You in the little situation, you always have the number of in little sodium hydroxide, that the number of OH minuses is always going to match the charge. And the same with the little ammonia, since the 2 little columns are always the same. That's a great rule. This makes everything so much easier. Now the excesses become a bit more complicated. We'll look at each of those in turn. But you can actually start looking at these equations now, guys. I hope you have a nice rest of your day, and I'll see you all soon. See you later, guys. Oh. Hey, see you later.